Let me share first my screen and then. So uh, today we are going to talk about design of cyclones for gas-solid separation. Some of you, fortunately, were in my mineral processing course, so you know that how we design hydrocyclones. So uh, it is very similar, I can say, but it is very similar, but there are some difference that is good for you to know. Uh, and also specifically, we are going to discuss about some specific design aspects for gas solid fluidized reactors. So it will add up to your previous knowledge in cyclone design. But I'm sure at the end, I'm not sure, but I hope at the end, all of you understand importance of cyclones, and at the end understand uh, um, how you can put all ingredients of course that we taught to you to design a good reactor, good reactor. Are you ready to go? Ready? Okay, let's move on. So let's in, start our chapter by FCC process. Anybody knows what is FCC process in refineries, in oil refineries?
We use catalyst and heat to create some chain of carbon-use material and then converted them to the light carbon-use like methane, ethane, and other fuels.
Yes or no? But what does FCC stand for? FCC is a very important.
Fluidized
Uh,
catalytic cracking.
Fluidized cracking catalyst
Yeah,
reactor.
what he says. What he said.
yeah, fluid catalytic cracking. Both of you were right. Fluid catalytic cracking. So FCC in an oil refinery is one of the most important processes. In fact, almost 50% of gasoline that you use to fuel your car, okay, is produced from FCC process. It's fluid catalytic cracking. So it's one of the main producers of gasoline. Right now is important. In future, if you are gonna have everything electrified, electric cars, whatever, maybe FCC will not be important anymore. Or still, it is very important because it's the main, one of the main processes. Almost 50% of gasoline is produced by FCC. But why I'm talking about FCC? Because FCC is a kind of circulating fluidized reactors where we have two main reactors, two main fluidized reactors. But let me explain how it works, and then step by step, I get to the point about cyclones. So let's start from here. In FCC, we have one column, as you see, is just a tubular column. This column goes up to here. This is the shell, kind of shell, but the main column is this one, internal column. This is called riser. Is a riser in FCC. So the feed here, which is usually vacuum gas oil, is the kind of is the oil cut from bottom of vacuum distillation tower in refinery. Usually, it can be anything, but usually it's that one. The feed is injected to the bottom of a riser, okay, and then with the high gas velocity that is injected from somewhere else to the bottom of the riser, the feed uh, here gets mixed with the catalyst that comes from this line. Okay, we will talk about later, and goes high very fast. If you remember at the first session, we said usually gas velocity in the riser is even sometimes 70 meter per second, very fast. So in other words, in this tubular riser, we have a fast fluidization regime. So the reason that the reactor is too fast is because, first of all, we would like to have a plug flow. Okay, there are two main reasons, and I want you to pay attention because it could be in your exam. So first, the high velocity is that in this tubular riser, you have a plug flow model, plug flow regime. If you remember, we said one drawback of bubbling fluidized bed is the back mixing. So if you don't want to have back mixing, it's better to have a high gas velocity so that the regime is like a plug flow. So this is the main reason, first reason. Second reason is the FCC catalyst, the catalyst that is used, is not very stable in terms of activation. The catalyst gets deactivated by the cokes because the carbon that comes from the feed. The, remember, I said the feed here is the vacuum gas oil, is a very viscous, and the bottom cut from the uh, uh, vacuum distillation tower in refinery. So it's a very um, dense, kind of dense fuel where the carbon to hydrogen ratio is quite higher. I mean, it has more, the carbon content is high. Therefore, the catalyst becomes deactivated by the carbon that's produced in the inside the riser, and you need to very fast recover your catalyst and send it to a regenerator to remove the carbon, and then after the catalyst is regenerated or reactivated, send it back to bottom of the riser. So this is the riser that is the fast fluidization. So what happens after the feed is injected? The gas, I mean, products are produced at the top of the riser. For all the let's say hydrocarbon products are outside, they are out, and then they're out from here. Everything goes into a cyclone. There is a cyclone here in order to recover, to separate uh, hydrocarbon products from catalyst particles. So catalyst particles, they uh, spiral inside the cyclone, then they collected. I mean, they're getting added to this zone of the FCC reactor. Then the remaining gas and other solids that could not be selected in the first cyclone, they go to the second cyclone. So there is here in this second cyclone, hopefully most of the uh, so deactivated catalyst particles get almost fully separated from the hydrocarbon products. So hydrocarbon products from the top, they go out, they go to downstream purifications, and then the remaining solids are collected here. So you see there are two cyclones here. In one cyclone, we have a primary cyclone and then secondary cyclone. Because it is usually the case, yeah, we don't have, sometimes we don't have just one cyclone. You have more than one cyclone. And cyclones, this is the representative, but even, I mean, this primary cyclone itself could be more than one cyclone. I mean, it could be two cyclones or three cyclones in parallel. Okay, so and then at the exit, all the inlets are integrated in one line, and then that line goes into secondary cyclone. But the secondary cyclone also can be in more than one cyclone. I mean, it can be two or three or even five cyclones in series, which is not which is the case of this our discussion today. We will see that at the end. But for now, imagine that there is one primary cyclone, and then I mean, in the primary cyclone, most of the larger particles are collected. Usually finer particles that could not be collected in the primary, they are carried over with the gas. They go to secondary cyclone, and then they recover products out. Other fine particles are collected to the this zone of the FCC, which is called a stripper. Okay. So if you just pay attention, the bottom of the, so this is the cyclone. You see that it has a kind of cylindrical barrel, and then there is a conical section below the cylindrical barrel. But then there is a pipe after conical section. This is called deep leg. But then there is a kind of valve. It's like a um, how to say flipper valve or kind of um, check valve. You may consider it just to make sure that the solids they go out, but the vapor they don't get inside. It just so these are two different type of valves that are put at the bottom of the plate to make sure that only solids go fall down. By the way, then everything, all the deactivated catalyst particles, they are collected. Then they travel down this stripper zone. So this stripper zone is a kind of area where we give more residence time to vapors that may not be fully some vapor that may not be fully recovered in the cyclone. Some vapors could come down. So therefore, we need more resistance time to some hydrocarbon vapors to go out. So this is steeper because of that reason. Also, the thing is usually some catalysts, okay, that are collected here, they are coated with some hydrocarbons, some non-converted hydrocarbons, for example, like a liquid film, you may assume. So they give some residence time also for those kind of liquid film of hydrocarbons around solid particles to evaporate and then go out from the top of the reactor. So this stripper basically is to make sure that solid catalyst that you uh, collect at this point is free of any hydrocarbon. Uh, so after all solids are stripped out from the vapor, hydrocarbons, and the vapors, uh, they they are transported to a regenerator. In the regenerate, so this transportation line, okay, where we have mostly solid particles, is called a standpipe. Standpipe. Okay. So then there is a valve here. This valve is to control flow of the solids to the standpipe. If you remember yesterday, we talked about choking. So this could be one case because if you send your if you send all the solids with the free flow rate to the regenerator reactor, maybe you end up with the choking here. If you remember, we said choking is uh, when especially uh, you reach a saturation flow rate of the solid compared to gas velocity that we have in the regenerator. So at the end, the bed will be dead. So in order to avoid the choking inside the regenerator, you need to have this kind of valves to just control flow rate of the particles. So after solids are transported to regenerator, then it's time for regenerator reactor. This regenerator, basically, what it does is to burn carbon that is deposited on the surface of catalyst with air. So in fact, it's a combustor. And usually, this regenerator is a fluidized bed operating under bubbling fluidized bed. So just as a reminder, in the riser of the FCC, you have a fast fluidization regime, but in regenerator, you have bubbling fluidization regime. Okay, so what happens is that you burn all the carbon. So in your flue gas, you have CO, CO2, and some vapor and water vapor that get out, and the regenerator catalyst is collected at the bottom of the regenerator and is sent back to the bottom of riser. through another standpipe. Again, in this standpipe, you have a valve, and this valve is to control flow rate of the solid to the bottom of the standpipe in order to avoid any choking in this zone. Okay, so if you see in this regenerator, also we have one cyclone. In here, for example, in this case, you have one only one primary cyclone as opposed to riser or top of the riser. So all the gases they go inside. I mean, after TDH, you have all the mixture of gas and solids go to the inside of the cyclone, and after all the solids are collected at the bottom of the cyclone, is they are transferred to the dense bed through this pipe, which is also a deep lake. So you can see that in the cyclone, we have a kind of a barrel, cylindrical barrel, a conical zone, a conical barrel, I can say, and then a kind of deep lake. See, there is a deep lake. It's just to transport the fluid, I mean, the solids from collected inside the cyclone to the dense bed. So at the end, what you see, you have a circulation fluidized bed. You have two fluidized beds, but the solid particle is circulated between two fluidized reactors. One of them is fast fluidized reactor, one of them is bubbling fluidized reactor. But in this process, cyclone is extremely important because if you don't design a good cyclone in FCC, you lose a lot of catalyst. You can lose the catalyst in riser, and also you can lose catalyst in regenerator. So it is very important to make sure, to design a very good cyclone to preserve all almost more than 99% of the catalyst particles inside uh, uh, inside the loop between the riser and regenerator. Okay, so anyway, uh, just for your information, I am schematically showing you what happens in the two reactors. So in the riser, in fact, the main reaction occurs where you crack the vacuum gas oil with the catalyst, and you produce some coke. This coke deposits on the surface of catalyst. But this reaction here is more endothermic reaction. You need heat, so you consume heat. But where do you supply the heat? Interestingly, you supply the heat from the regenerator. So in regenerator, you burn off the coke deposited on the surface of catalyst, and as a result, the catalyst that you have regenerated is very hot, and this catalyst, after it's transferred to this to bottom riser, is hot enough to supply the required heat for their reaction. But something very interesting. I said this valve that we have in the standpipe is to control flux of the solid into the bottom of the riser to avoid choking. But we have to also pay attention that we need to have enough flow rate of the solid also to keep the oil riser at the right temperature that we want. If you reduce the flux of the solids, if you reduce too much, maybe you won't have enough energy inside. So you know that energy is mCp delta T. So mass of the solid is important. You cannot manage. That's why FCC is a very complex process, uh, and it requires a lot of engineering, design, and research activities. So in the world, there are few companies who have the license of FCC. One of them is IFP. It's the institute. It's the French Institute for Petroleum. It's Institut Français de Pétrole, if I'm not wrong. So IFP and Total, in fact, they are licensing FCC process. There are other companies like ExxonMobil, like UOP, and also, of course, Russia and China. They have their own processes, but they are mostly copy of IFP and ExxonMobil processes. So you see the what is the, in the you see in this slide how cyclones are important. Because if you lose particles from the from the top of the cyclone, if you lose catalyst, these standpipes that you have will be in trouble. Because, for example, here you may have less flow to inject to the riser to the regenerator, so your regenerator bed height could decrease to come here, for example. So as a result, the deep lake will be above the surface, which is not the case. Usually, we want to have the deep lake in bubbling bed inside the dense bed. So to control level of the dense bed here in the regenerator, we need to have enough flow rate of the spent catalyst. So to make sure that we have enough flow rate, we need to have a good collection of the activated catalyst via cyclones. Did you get the point about FCC? Java, did you get it?
Yes, sir.
No? If I
Yes.
a lot of I mentioned a lot of points. I know this, but I'm just emphasizing
Yeah, I took a note.
importance of cyclones, because it's not, maybe schematically you don't understand the points, but when you touch each point has a lot of technical information that I want you to pay attention. As if you don't, for example, the last point that I mentioned, if you don't collect all the particles from the cyclones, so you don't have enough flow rate of the solid in this standpipe. As a result, you don't have enough material here, so the level of the dense bed could decrease to somewhere here. So as a result, this deep lake will be above the dense bed. But if you do that, it's not a good kind of design. Why? Because if you're let me show my hand here. Because if the dense bed is here, let's say the surface of a dense bed is here. If you remember, we said yesterday we have some ejection of the dense at the surface of the bubble, some ejection of clusters. These clusters, uh, they will also touch these returning particles, so they carry over all even the particles. So these particles that are supposed to come back to the dense bed, they will bypass and then they go upward. So the efficiency of the cyclone will deteriorate. Therefore, it is important to make sure that the level of the dense bed remains above the bottom of the deep lake. We are going to discuss it in more detail today. Okay, so this is our importance of cyclone in one of the most important refinery processes. Okay, so this is the kind of schematic of typical FCC cyclones. If I already talked about these two in FCC, usually we have a terrain of primary cyclones and a terrain of secondary cyclones. So this primary cyclone is directly attached to the riser, and this cyclone is attached to the outlet of the primary cyclone. So about the geometry of the cyclone, there are different designs, but most often they are quite similar. For example, uh, about the entrance of the gas to the cyclone. If you pay attention to this picture, uh, when the gas wants to get into cyclone, it gets into cyclone through a kind of rectangular opening. It's a rectangular opening. It's not circular. It could be circular too, but mostly it's rectangular. Okay, because of the hydrodynamics and many things, they have they, they tend to be um, rectangular. Okay, so the gas gets in through this rectangular opening or inlet, I can say, and this rectangular has a height and has a width. Then the gas gets inside the cyclone. So cyclone part it has a upper part. It's like a cylindrical barrel, and the gas inside travels some kind of spirals. Okay, like this. We will see in the next pictures uh, better schemes. At the bottom of the cylindrical barrel, there is a conical barrel. Okay, this conical barrel, uh, you see, it has an angle. For example, if I show the angle here, let's say alpha. This angle is important. Why is it important? Because when you let's say your solids gets separated from the gas stream, the solid that you have, they are supposed to fall down, but some particles, okay, they sit on the wall of the conical zone. Okay, if you remember in your, the rheology of the particles, we said there is something that's called angle of repose. So you want to make sure that particle you have an angle, okay, that you have an angle that meets the requirement for your angle of repose. If you have an angle here that is more than angle of repose of powders, they will not fall down. Okay, so that's this angle here is very important, and uh, it's something that you need. I mean, there are some equipment, of course, that are there at the lab to measure rheological properties of each powder. So this angle has a is important, is selected with respect to angle of repose of the powders, because you want to make sure that all the powders sitting on the wall, they can fall down. Okay, so after all the solids fall down, okay, then you see that there is this kind of volume before deep lake. Deep lake starts here. This is the external pipe. This is just a kind of a safety volume, to make sure that you are not choking the deeplet, because you don't throw everything right away to the deeplet. It's a kind of you can assume a kind of not secondary cyclone. It's not really a cyclone here anymore, but it's like a expanded zone and then a conical zone to just manage flow of the solids to the it's like a funnel, funnel. In Persian we say pif for some of your Iranian funnel. It's like a funnel. It's just to help solids to fall down so they don't choke inlet of the deep lake. Okay, so it's a kind of safe zone below. But it's a design option. Maybe you don't have to do that. It depends on your powders. Okay. For FCC, they do it like this. Okay. After solids are collected, usually the gas tends to, after the gas reaches somewhere at the bottom, the gas reverses its flow and then it starts to go up. Of course, the upward flow also has a kind of internal spiral flow. or internal vortex until everything goes out. So inside the barrel, cylindrical barrel, there is a kind of internal tube, which is for to help uh, the gas exit uh, from the top of the uh, cyclone. In next picture, we have better representation. By the way, just I want to draw your attention for these letters that are you see here. Uh, People show dimensions of the cyclones with different, I mean, abbreviations or different letters. Um, you will see the next slide that we have some different letters, but uh, don't worry, we have um, enough explanation in the slides that so you can understand uh, which one is which. For example, uh, here in this picture, the height is shown by HE and the width of the inlet is shown by LE. But for example, we can show in next slide this height just by H and here by LW. There are different, letters, but don't get confused. Basically, everything is the same. So you have the inlet of the gas, then you have a spiral flow of the gas inside. You have a cylindrical and conical zone, and then you have a reversal flow of the gas in order to exit through the exit pipe, and that's it. So this is basically structure of a cyclone. Okay, but inside the FCC, since I talk about FCC, let's also show you some designs in terms of configuration of riser column with respect to cyclones before we go to details of the design and political aspects of the cyclone. If you remember, I said we said that inside the riser, inside the FCC, you have one riser where gas is with a very high velocity. It's a fast fluidization regime. Usually, in order to uh, better help having less cyclones and to have less cyclones and also to have better efficiency of the cyclones. As you see, first of all, you have kind of expanded diameter. See, you have this kind of expanded diameter in order to, as we said before, in order to reduce velocity of the stream, so that some powders they can fall down. But also there are some barriers here that is called disengager. Disengager. These barriers also help to recover some solids even before they get to this kind of dilute phase. So these are some aspects just before cyclones. But these disengagers, they can have different designs. This is a simple disengagement. In here, you have a kind of riser separation. So this riser is splitted into two these kind of geometries. So hydrocarbon vapors are separated better from the deactivated catalyst, and then everything goes toward the cyclone. And in this design, these geometries, these kind of I can say lateral pipes beside riser, they are directly connected to the cyclone. Okay, so in this design, the gas is released to this open area. Okay, so the chances that some particles fall down. Okay, due to reduced velocity. Uh, but in this case, powder directly get into cyclone. So these are all different designs. Depends on the size of the FCC catalyst. Depends on uh, conversion rate depends on attrition of the powders, agglomeration of powders, many other things. But I mean, I'm just showing you that before the gas stream that contains some powders gets into the riser, you have some design features inside the expanded zone. So you have expanded zone and you have these kind of disengagers. Okay, now let's start talking about theoretical aspects of cyclones. So I guess already you got an idea what is a cyclone, right? Anybody here didn't understand what is a cyclone? Muhammad Khaji, did you understand what is a cyclone?
Yes.
Nushin? Because some of you are.
Yes.
So, Henok, did you get what is a cyclone?
Yes.
Did you see the importance of the cyclones, right?
Yes, I see that, but I have just one little question.
Yes, sure.
We put the disengagements at the upper part. Do we consider attrition when we put this thing?
Yes, of course, of course. As I said, all these designs, very good question. All these designs are uh, should be selected based on different parameters. Definitely, this simple disengagement, this one on the left, could behave like an impactor. I mean, it can break particles, so you can attrit particles. But in this design, you may not have attrition, or you may have less attrition. Very good question you mentioned. Of course, I mean, as I said, this expanded zone has a lot of features in terms of attrition, in terms of agglomeration, in terms of um, uh, velocity of the particles, in terms of concentration of the particles. Because if you remember yesterday when we discussed about design of the freeboard, we said at the end what we want from a freeboard is three things. First is to measure the TDH. Second, to measure flux of the solids above TDH. Third, size distribution of the solids above TDH. Right. So all of these are important to select this engager.
Excuse me, Professor, what was the first one?
TDH. Okay. First, usually the case of TDH is usually for mostly bubbling fluid that is bad. In riser simulators, maybe TDH really is not. There's a fast fluidization regime, but anyway, the first is to measure TDH. You need to know what is TDH if you have bubbling fluid that is bad regime. After that, beyond TDH, you need to know what is the flux of the solids in the gas stream. Remember yesterday we talked about F infinity, the infinity sign. It was we were showing this parameter F infinity. It was the flux of the solids in the gas stream beyond TDH, and also we had to know what is the size distribution of the powders beyond TDH. So all of them are important. Attrition, everything is important. So sometimes when you design upper part of a reactor, you have a trade-off. You want to recover some solids, for example, with this disengager. So sometimes you want to use this kind of disengager to help, but at the same time you may attrit your powder, so maybe it's not a good idea. So there are some back and forth. You need to do research to investigate each design aspect to select your best option. By the way, these kind of impactors or disengager, I it's a kind of subject of maybe a PhD project. A few years ago, we had one student. His whole PhD was about this kind of impactors in order to de-agglomerate agglomerated particles. It was the same thing because here you have a high gas velocity, and this high gas velocity touches the surface of this disengager, and then uh, how those could be affected, or if they're agglomerated, they could be de-agglomerated. So I don't want to go beyond the course, scope of the course, but anyway, I mean, all these designs are selected based on a kind of research and development activities. You have to see all the options on the table and investigate them, see which one is the best one. Did you get your answer, Henok?
Yes, thank you.
You asked a small question, but I know I explained too much.
Thank you.
But I hope you guys follow important topics that we have here. So let's now talk about cyclone. In fact, cyclones are centrifugal operations that rely on centrifugal forces. Okay, so inside cyclone, you have centrifugal forces. So as a result, the small particles which could not settle in a reasonable time under effect of gravity, uh, I mean, inside the freeboard, they can settle very quickly when submitted to a centrifugal field because you have acceleration, centrifugal acceleration, so um, they get kind of blasted and it can be separated. There are various types of centrifugal operations. For example, centrifuges, centrifugal filters, cyclones, and hydrocyclones. So, in fact, cyclonic operations, I can say, even there are reactors that operate like we call them cyclonic reactors. They operate inside the cyclonic system. So all of them are based on centrifugal operations. So for specific applications, you may require other equipment beside the cyclone. I mean, uh, um, so then you make a kind of separation train. It means maybe you have one primary cyclone, then you have a secondary cyclone, but still you see that after secondary cyclone, still you have some dust. This is the case when you work with very fine powders. When with these days we talk about nanoparticles. They are very dust, so maybe cyclones are not very efficient. So in this case, for example, after all the cyclones, you need to have, for example, electrostatic precipitator like this one, or you may have specific cyclonic, for example, scrubbers, or specific filters or demisters. Sorry, not demister, dusters. So there are different options that we can have beside the cyclone. But right to today, we are assuming that we are going to design cyclones where more than 99% of the powders could be recovered from the gas stream. But keep in your mind, this is important because right now at our labs, we have this issue that we need to have other equipment besides a cyclone. Well, some of you are going to work on phosphate ore project. I think Muhammad Khajri and Ahmad Najjar, I guess. So yeah, since we are dealing with uh, ore materials, and they become very small particles, and specifically there are some heavy metals that are toxic like cadmium, mercury, and others. It is very important to make sure that even after cyclones there is no trace of these very fine particles. So in pyrometallurgical industry, they use electrostatic precipitator or specific filters to capture those very fine powders that could not be collected in cyclones. Okay, cyclones are, I mean, cyclones of the course of today, and we are talking about gas solid cyclones. Cyclones are used mainly for separation of solid particles from a gas, mainly. Although that may also be used for separation of liquid droplets from a gas or vapor. We are not talking about hydrocyclones. In hydrocyclones, usually you have a huge amount of liquid fluid, like water. Here we are saying that, for example, in some gas solid fluidized reactors, maybe one problem is not just the not just particles, even some droplets. So in other words, you can have some cyclones to separate solid particles like catalysts, but after that cyclone, you can have another cyclone to capture the droplets of the liquid. This is the case in, for example, oil cracking. For example, myself, when I was doing my PhD, I was cracking bio oil in a gasification reactor. And always at the outlet of my cyclone, I had some very fine droplets of bio oil, which were not converted. But since they are very fine, like maybe 1 micron, 2 micron diameter, they are still there. And if you don't collect them, if you don't capture those liquid droplets, they can go to downstream application for equipment like condensers, pumps, or compressors, whatever. And after a while, they build up a film of liquid, so they damage your equipment. So this is something, this is kind of important information that gas solid cyclones that you design, maybe you should design a second type of cyclones for the droplets of the liquid that to be collected. So as I said before, cyclones are often arranged in a train like a 2 or 3 cyclones in series with cyclones of increasing efficiencies. So you can have primary cyclones, secondary cyclones, and tertiary cyclones, for example. Usually, tertiary cyclone has efficiency higher than secondary, and secondary has higher efficiency than primary cyclones. But as I said before, each series of the cyclone could be more than one cyclone in parallel. Okay. So the efficiency of a cyclone can be increased by either increasing the capital cost, for example, by using several smaller cyclones in parallel, as I said for this sentence. So you have this kind of multi-clones. So this is the capital cost. If you, instead of one cyclone, you want to split the inlet flow rate to 2 or 3 streams. So you have 3, for example, primary cyclones working in parallel. But you add the capital cost to your process. Another option to increase the efficiency is to work on operation cost. So you can have higher cyclone inlet velocity, which usually improves the performance. You can design a cyclone where you have higher gas velocity into the cyclone, but you know that that will cost you pressure drop, and so it's about operation cost. So this is an example of 3 primary, secondary, and tertiary cyclones working in series. You can see that usually the the inlet of the primary cyclone is the outlet of the secondary cyclone, and the outlet of the secondary cyclone is the inlet of the tertiary cyclone. And each cyclone for this reactor, which is a bubbling fluid as well, has a deep leg, and usually all the deep legs are immersed into the dense bed. And this is just a schematic of bottom of a deep lake. So usually at the bottom of deep lake, you have a kind of inclined small pipe, and then there is a kind of flapping valve, or I can say check valve, whatever you call it, or just a on and off door, whatever you call it, in order to control flow of the particles to the bed, and at the same time uh, minimizing the backflow of the dense bed into the deep. So the scientific action, we said this, sorry, we said this cyclones are they operate based on centrifugal forces. So how this centrifugal forces is generated? The centrifugal action is created by spinning the gas with one of two techniques, either by tangential inlet, which is usually the case in regular reverse flow cyclones, as we showed for example, in these pictures. For example, you see that the gas gets in through a kind of rectangular inlet, which is really not exactly to the in the center of the barrel. It is beside, so it creates a kind of tangential flow of the gas inside. Okay, so the gas gets in, uh, not perpendicular to the column, but kind of with a tangential direction. Another way of creating centrifugal action is by using vanes. For example, in this picture, these vanes are kind of fixed fittings inside the pipe, for example, like a static mixers. So these vanes have a special design. When the gas gets in, it will have a kind of tangential flow from here and tangential flow from that internal zone. But this is not very common in food as well reactors. And one problem of this kind of centrifugal action is that powders, they can erode these metallic pieces and they can be damaged. So this is a better presentation of a cyclone. So you see that the inlet of the cyclone is not here. If you imagine this kind of a circular cross section of the cyclone, the inlet of the gas to the cyclone is beside it. Is not like something like here, perpendicular to the circular cross section. It is designed really here in order to create that kind of tangential flow. As a result, I showed you before, you have this kind of spiral flow or kind of vortex, okay, until the gas reaches a point where the gas tends to reverse its direction and then have another type of vortex or a spiral flow, okay, which is usually smaller and until it gets out. In terms of some advantages of cyclones, first of all, since they are based on centrifugal force, the usually efficiency of separation of solids at the bottom of the cyclone from gas is very high. Usually, pressure drop in cyclones is low, and they can operate for high throughput, high capacity, and they can operate in continuous mode. Okay, so they are very interesting mechanical system. But in my opinion, one big advantage of cyclone is that you don't have any rotating system. You don't have a kind of mixer, nothing. It's not, there is no, you don't have to use any power to mix something. That spiral flow is generated just by natural flow of the stream that contains powders and solids. But of course, there are some limitations in terms of cyclones. You need to have a very careful design. So you cannot just underestimate, I mean, under design or over design your cyclones. It's better to research and development activities to make sure that you end up with a good design. And also, if you have very fine powders, like less than 5 micron, usually they are not very efficient to separate these powders. So that's why I said sometimes it's good to have other equipment after cyclone, like filters, electrostatic precipitators, and others. This picture shows
Sorry,
you.
excuse me.
Sure.
Sorry. On the previous picture.
Yeah.
Yeah. So it says low efficiency for very fine particles. What's the reason for that?
Usually in cyclone, uh, the usually I mean general, finer particles are more difficult to be separated usually. Okay. Why? Because finer particles they tend to be close to the center of the cyclone. Okay, and then they can be re-entrained by the backflow of the gas and get out. Because we are going to discuss it. You see that this kind of a spiral flow. In fact, in reality, it's not just one line. You have okay. Do you know what is the name of this planet? You know Saturn planet in our
Oh yeah,
solar
yes,
system.
yeah,
In Persian, we say Zohal, Saturn planet. It has a ring around it. It's not
yes,
just one ring. It's a that ring is in fact the dust or ice, kind of ice and dust, everything mixed together. But in fact, it's the several rings that they can create that big ring around the Saturn. It's the same thing here. This line, for example, is just showing you one of the spirals, but in fact, you have outer spirals and internal spirals. You have a couple of spirals that are creating the overall spiral flow. Usually, finer particles they tend to remain inside. I mean, the central spiral. Okay, so it's very likely that those finers they get re-entrained with this backflow of gas and they get out. Did you get the point?
yes. Thank you.
So yeah, Robert. But we asked very good questions today. keep keep the notes, guys. That was a very really good question. Um,
Um,
yes,
excuse me.
sure.
Can we have a break?
Okay, of course. Let's have a break
Thank you.
for 15 minutes. Not for 15, yeah, 15 minutes. Let's be back at 2:42. Okay?
Thank you.
You're welcome. Okay. Nushin, are you here? Nushin? Okay, she will join. Okay, so regarding cyclone, uh, here there is one experimental setup. Let me just change my pointer. This is the kind of experimental setup to investigate efficiency of solid separation from gas for specific research. You can see clearly these spirals. You can see that these spirals look like that, and it's very clear. If you look at, first of all, what you see in this picture is that first of all you have several turns, 1, 2, 3, 4, 5, 6, almost 6 kind of turns of the spiral. Okay, the number of the turns that you can generate is important, of course, in the efficiency of system. Another thing, as I said last time about Saturn planet, you see that each, if you look at each turn, there is a width. There is a width for each kind of a spiral. So it's like a quite flat, maybe let's say 2 centimeter, 5 centimeter. So you have, you don't have just one very thin line. Exactly, it's like a ring or just a rope, I can say. Like it's like a rope that you see that that is like a spiral inside the cyclone. This is a picture from a top view picture from a circular uh, uh, cross section of the cylindrical barrel. You can see that the gas exists here. When the gas exists here, at the entrance, there is a kind of disturbance or interference between the inlet gas and the gas that is already being centrifuged. So this is the kind of interference that can impact the efficiency of the cyclone and also pressure drop, but this is the case that is always there. Just so I want you to just know that. Another thing that you see, you have one internal or inner vortex, and you have, so this is the outer vortex, which is mainly uh, in the main cylindrical barrel, but then also you have inner vortex, which is usually the vortex which is smaller inside the exit pipe. But interesting, you see that the direction of the vortex is similar to in both of them. I want to say something also that when they pay attention that the feed that gets into the cyclone is gas mixed with solid. Okay, it's not just solid and it's not just gas. Okay, I just want to pay attention that in terms of the cyclone is a mixture of solid and gas. Of course, yesterday we learned together how to design a freeboard to minimize concentration, or in other words, a flux of the solids in the gas stream. But at the end, still there could be some particles that come in. And as soon as particles gets into the barrel, okay, if you want to have high efficiency, it's important to make sure that all the solids, as soon as they get into the barrel, they travel or they migrate to the internal wall of the cyclone. That's really important, because as I answered to Henok, if some powders they remain in the internal areas of the cyclone, they can be re-entrained by the backflow gas in the exit pipe, and so the efficiency of the cyclone will be bad. So it's important that as soon as the solids get into the cyclone, they migrate to the wall, get close to the wall of the cyclone. In this way, the efficiency of cyclone will go higher. Based on what I just said, there are two terms we are going to define. One is drift velocity, centrifugal drift velocity. It is the velocity at which the particles migrate toward the wall. As I said, so when particles are inside cyclone, they tend to migrate to the wall, and the faster the better to have the high efficiency in the cyclone. Another term is residence time. It's very clear. I already, residence time in overall is the time that takes for the solid from the inlet until the collection. So in other words, we can say it is the time spent by the particles in the outer spiral of the cyclone. It's just more specific that says the outer spiral of the cyclone, okay? Which means inside the cylindrical barrel and closer to the wall. And this residence time represents the time during which the particles have to reach the cyclone wall where they can be collected. So it means in general, the whole time that the outer pipe out solid is there until it's fully separated from the gas that is going to be back. So we are going to define some formula to measure drift velocity and residence time. Very easy to understand. So the distance, first of all, about residence time, because first we need to know residence time. We will see later why. The distance traveled by a particle spiraling down the cyclone, okay, is very clear. It's number of the term divided by pyramid inside the barrel. So 2 pi RC NC. RC is the radius inside the barrel. Okay, but of course this is a rough approximation because this simple assumption considers only particles which are near the wall. It doesn't consider particles that are closer to the central radial positions. And also it neglects the conical part of the cyclone. We know that it assumes that everything is just a cylindrical, but this is just one term that is easy to define. So there are two other assumptions. First is that in terms of spiral velocity, cyclone inlet gas velocity should be clear. We should decide something for the inlet gas velocity inside the cyclone. Okay, which and we know that since in the lower section of the cyclone, which is the conical part, we know that the velocity will be higher because you have less and less cross-sectional area. So when we say uh, spiral velocity, we are assume that the spiral velocity is equal to inlet gas velocity in the cyclone. So inlet gas velocity, we know already gas flow rate into the cyclone. If you know cross-sectional area of the rectangular inlet of the cyclone, it's easy to uh, to calculate VI. But this is something that you can assume also because sometimes we measure. It's better to assume a value for VI and then size the cross-sectional area of the cyclone. You will see the procedure later. I'm saying this rectangular inlet that you have, it has width and it has height. Maybe for some reasons, for example, you are given with the cyclone, there is a company that already has designed a cyclone, it just gives to you. So you have no option. You can just calculate what is the inlet gas velocity. But when it is your own job to design a cyclone, usually the case is that we first fix a value for velocity inside the cyclone, and based on which we design dimension of the entrance of the stream, of the gas solid stream. Okay, so keep in your mind. So another thing is that velocity of uncontrolled particles that are could be maybe not in the really in the spirals, not really close to the wall. We can assume that all particles they have a gas velocity of VI. So because they are quite negligible, those uncontrolled particles. You cannot really. Uh, it's not easy to measure the exact velocity. So by knowing the inlet velocity of the gas, okay, and also by knowing the distance that the particle should travel, we can just easily have this estimation for the resistance time. So residence time is two times of radius, which is diameter, and then multiplied by pi, number of the turns divided by inlet gas velocity. Very simple equation. But now about drift velocity. So to measure drift velocity, there is a very simple force balance inside the cyclone. So imagine that a particle is traveling um, on the internal wall of a cyclone. Usually there are we consider two forces. Uh, we consider two forces that are prominent during the travel of the particle. One is centrifugal force, which is toward the center of the cyclone. One is the direct force, which is toward the wall of the reactor. Of course, the particle has also weight force, but that's negligible compared to these forces. So we just consider these two forces. Okay. So if we assume that uh, the net centrifugal forces is balanced with the direct force, okay, during the travel, we can just easily write the related correlations as shown here. So you know that net centrifugal forces is roughly, we are saying mass of the particle minus mass of the gas divided by multiplied by centrifugal acceleration, which is v2 divided by r. So v is the tangential velocity at which the particle is turning, and this term is the direct force. So pay attention, the direct force, uh, we know that first of all, direct force is applied to surface area of the particle, but centrifugal force, similar to weight force, is applied to volume of the particle. This is important because sometimes in some conceptual discussions, we forget how forces are felt by particles. So drag is something that is applied not to volume, to the surface of the particle. Okay, just keep in your mind. And it is governed by the drift velocity, because it is by the, as if you remember, drift velocity was the velocity by which a particle wants to migrate to the wall, toward the wall of the uh, toward the wall of the cylindrical barrel of the cyclone. So by assuming that the particles are spherical, you can have this ratio for the volume of particle and this ratio for volume of for the surface of the particle, and put into this equation. And eventually you calculate the drift velocity. Very important information here. First, drift velocity is the velocity of if the velocity that the particle wants to travel uh, toward wall of the cyclone, okay? But v is a tangential velocity at which the particle is turning on the internal surface of the cyclone. So I can say this is the turning velocity. Drift is a kind of radial velocity, drift velocity. So you should know the difference. But the most important information is drift velocity has direct relationship with the diameter of the particle. Back to Henoch's question. If you have larger particles, you have higher drift velocity. So larger particles, they get faster to the wall of the cyclone. But the smaller particles, they have a smaller velocity, a smaller drift velocity to get to the surface of the cyclone. And this is why when finer particles, when particles are very fine, so since the drift velocity is low, they cannot be maybe they cannot be close to the wall of the cyclone. As a result, they can be entrained by the backflow gas in the exit pipe and then up. So this is really the answer to Henoch. This is why finer particles are more difficult to separate because they have a lower drift velocity. Another thing,
Yes, thank you.
yeah, okay. So another thing is the radius of cyclone. Okay, so you see that if you have a smaller cyclone, you have higher velocity, drift velocity. You remember we said if you want to increase the efficiency of the cyclone, is better to divide into two or three parallel cyclones. Is because when you have a smaller cyclone working in parallel, so you generate the bigger drift velocity. So and since we know drift velocity is about having particles on the surface of the on the wall of the cyclone, so and those particles on the wall will be collected with higher probability. Therefore, this is the reason having smaller cyclones. I mean, for example, having a couple of smaller cyclones in parallel maybe is better than one bigger cyclone. So this equation has significant information: radius of the cyclone, diameter of the particle, and the fact that we have two different velocities in this equation. Be careful. But what is the value of v, spiral velocity? What is the value? The tangential particle velocity is usually close to the gas inlet velocity that we usually fix at the design step. So therefore, sometimes we just assume that tangential velocity is similar to inlet velocity. Okay, and to be on the safe side, we can take the largest possible value r, which is the largest radius of the cyclone, which gives you the smaller drift velocity. By the way, I'm just saying let's take the r because we want to have a new correlation for drift velocity. Let's say, uh, let's say what we want to see what should be the uh, uh, minimum drift velocity that we can have in the cyclone, and then you will see the later discussions. Also, since we are talking about uh, small particles in the system, usually, first of all, particles that get into cyclone usually are the smallest particles since they have a low terminal velocity. Second, also we know that uh, among these small particles, the smallest ones are the hardest to collect. Therefore, for such particles, the Stokes law is applicable for Dirac force. Therefore, for the Dirac coefficient, we can write this known correlation. So if we put all these assumptions into the drift equation, we see that drift is equal to difference between density of particle and gas, density of gas, tangential velocity, particle diameter, and radius of cyclone for a specific cyclone. Okay, so this is the formula for drift. But now we are going to talk about something in the cyclone that is a kind of design parameter. Now it is called cut point, cyclone cut point. Back to the this correlation that we talk about fine particles versus larger particles and the impact in drift. In fact, the parameters defined as at the cyclone cut point, which means the smallest particles, okay, usually in the system is smallest particles that we have, 50% of them will be collected, 50% will be entrained by the gas flow in the exit pipe. But let's see how this cut point can be calculated. First of all, I have to clarify something here. Imagine that this is a cyclone, that the notation here is a bit misleading. In fact, imagine that this is the inlet of cyclone. This LW that is shown here is the width of the cyclone. So here is LW, and the height is H, the height of the entrance. The way it is shown here, I took this picture from one of my previous notes. It's really misleading. This H, I don't know why it's shown like here. This H is the height of the entrance, and this LW is in fact width of the entrance into the cyclone. Okay. Now, based on this assumption, you know that when a gas stream gets into the cyclone, so some particles are here, some particles are here. Now, in other words, some particles are really, when they get in, they are really close to the wall of the cyclone, and some particles are far from the wall of the cyclone, right? Because they are mixed, and this is what it is. Now consider particles which have farthest to travel before they reach the wall. I mean, let's consider these particles. So when they get here, they are at the farthest distance to get to the wall of the cyclone. Okay. So if they want to come, if they want to get to the wall of the cyclone, they have to travel this LW. This LW, because here is also almost LW. From here to here, they want to travel first. Okay. So one of these particles will be collected if it has enough time to reach the wall. So in other words, if I don't know why sometimes I don't see my change. Okay. Imagine that you have one particle here, and he wants to go to the wall of the reactor. You know that the particles travel from here to here by drift velocity, okay? And since the distance is LW, so the time that takes for the particle to come at the entrance from here to here is LW divided by drift velocity. And usually this is smaller than residence time, because residence time was about the total time that he's going to be in the inside the cyclone. But we are saying that the smallest particles, okay, the smallest particles, since they have very low drift velocity, their time to reach from here to here is going to be much longer. So the maximum time that they can have cannot be longer than residence time. So in other words, we say the smallest particles entering at LW, which we collected, are such that LW divided by drift velocity of fine particles, the smallest particles, is equivalent to total residence time inside the cycle. So this is one correlation that we just generated by that assumption. Okay. So by putting, so already we know the ratio correlation for TR. We have the correlation for drift. We say we obtain this ratio for the smallest particles that could be separated inside the cyclone. So again, so therefore, here now we have a correlation that tells us, okay, what is the size of the smallest particles that could be separated in the cycle. So the correlation is this one. but it's just this one. But you know, it is just by an assumption that even though we say that this is the correlation that roughly we can say tells us what is the largest size of the smallest particle that can be selected, that can be separated. But in fact, usually as a kind of uh, design parameter that is usually accepted by everybody in the cyclone domain, it is they say among these uh, 50 particles, among these particles that are the smallest ones, 50% of them will be collected and 50% will not be collected. Remember, this correlation is about the even though it's a DP mean, but it means then uh, it means the lowest particle that can be separated. In other words, the largest particle, uh, I mean, the particle smaller than this one is the largest particle that could not be separated. So, and also they say that, let me, I wish I could have something to write. Let me write something. I want, because this is kind of design thing and I want you to know. Let's say you have some particle that are, let's say, have a size of 10, 9, 8, and 7, for example, just a number. And you said, you did the calculation, you found that, okay, DP mean is 9. For example, particles of 9 micrometer, for example, will be collected with the larger particles inside the circle. But what about these smaller ones, 8 micron, 7 micron, for example? They say, but it is, they say that these other particles that remain as the smallest portion of the overall powders, 50% of them will be also uh, collected in the cyclone, and 50% will not be collected. This is a that's why the critical point uh, that shows you uh, uh, shows you that the smallest portion of particles, 50% of which will be selected. This size is called cut point of the cyclone. That's just the definition. So by definition, the cut point of a cyclone is the diameter of the particles which are collected with a 50% efficiency, which are usually the 50% of the smallest portion of the particles. I hope it's clear. If not, I can explain later. So when we say efficiency, what does it mean? Of course, it's very clear. It means mass of collected particles at the bottom of the cyclone divided by mass of particles entering the cyclone. Okay, so this is the yeah.
For your example, 50% of 9 micrometer can be separated, and 8 or 7 can't be separated.
No,
Yeah, they can be go to.
No, because you know, in if you remember when we said, if you remember when we said cumulative size distribution, remember, it's something like that. It says particles the smaller, finer than this size, particles finer than this size, okay, will be collected by 50% efficiency. Remember when we said in cumulative distribution, when we say, for example, DP80, DP50, something like that. We say, when we say DP50, 50% of the particles. The size of the 50% of the particles that are finer than that one. So the meaning is this. It means 50% of the finer particles uh, will be uh, collected, the other not. This is just a cut point definition. Okay. So this is about some definition for cyclone cut point for drift velocity and residence time. And now get back to design of a cyclone. Let's say now you want to design a cyclone. So there are several correlations, several, I mean, uh, design methods, but one of them that is accepted by many people is by Zenz. In fact, Zenz is a scientist who has done a lot of research in freeboard design, in cyclone design, and so he has a lot of um, work. So according to Zen's design, okay, the ratio between each dimension of a cyclone is as per listed here. So diameter of the cylindrical barrel is 4 times width of the inlet of the stream. Diameter of the exit pipe is usually half of the barrel, and height, h is height of the entrance, is 2 to 3 times of the length. Okay, and the rest is explained here. You can follow yourself. I'm going to go to this slide. In fact, besides Zen's model, which is usually for medium efficiency cyclones, there are some other models, like for high efficiency cyclones, or for if you want to have high efficient, or if you want to have a cyclone with high throughput, high capacity, I mean large cyclone, you can take these dimensions. So you see, the design of a cyclone is very straightforward. You just need to, start from somewhere, and by these dimensions, these ratios, find the other dimensions. But something that is very interesting in all these values is that usually they say it's better to have diameter of the barrel should, okay, to be 1 meter. Okay, if you are in term of a scale should be 1. I mean, if in your design it should be 1, you are in that scale should be 1 meter. It should be in that range. Okay, and the rest are easy, accordingly are found. But something I wanted to tell you is that these letters that I'm using here, I'm showing you here. Here's my pointer. Yeah, these letters I'm showing you, D, B, D, E, H, L, W, H, E, blah, blah, blah. In some other textbook could be shown by different letters, but at the same time, all are the same. For example, I'm showing you this graph. For this, it's also a cyclone design. It's also cyclone, but you see, for each geometry, other letters are used. For example, here they show DC. Here we were showing just by D, DB. Okay. Here it means a cyclone column, or some people say cyclone barrel. So, okay, so don't get confused about that. But anyway, these are all by also same researchers. Some of them are not here, but most of them are here. Same dimensions are reported. But let me tell you one important thing. When you want to decide a cyclone, you see that there is one length that is shown by LC, for example here. It's the length of the cyclone barrel, I mean cylindrical barrel. But then there is another length, which is the length of the conical zone, and it's showing by ZC. But and here in this table there are some correlations for ZC. So usually they say if you compare these two rows, almost lengths of the lengths of the cylindrical barrel and lengths of the conical zone almost similar, not very different, almost sometimes different. Here is the same, here is 2, here is 1.75, but almost similar. Maybe in this case it is a bit more different. But the thing is, personally, I think this height, you have to be careful when you size it. You should not just stick to information in these tables because of the rheology of the powders. As I said, the angle here that is made with the orifice, angle of repose has to be considered. If you have no information about angle of repose, you can use information in this table. But if you have the chance to measure angle of repose of the powders, you need to decide what should be the angle and accordingly calculate or obtain this length. Why? Because this diameter here that we have, ds, is more important than diameter of the than the size of the size here. I mean than the because this diameter, which is the diameter of the exit of the collected particles, is important. If it is too big or too small, you may have plugging, or you may have some kind of a stretch of the spirals into this zone. So this dimension is more important than ZC. So therefore, that's why I'm saying after you set the size of DC and you set the size of DS, okay? For example, you see DS over DC, it's better to then decide for the size of the length of the conical zone. Okay, this is my personal preference that I'm sharing with you. Okay, another thing about the design is this graph that helps you to find number of the spirals in the cyclone. If remember, I said you can set the velocity of the inlet gas into the cyclone. You can just select, you can pick a number yourself. Let's say you can say I want to pick 10 meter per second. So you said 10 meter per second for that velocity. You will have 3 spirals. If you want to have more spirals in your cyclone, you need to go to higher velocity. Let's say you want to say I want to have inlet gas velocity in my cyclone about 50 meter per second. So for 50 meter per second, number of the spirals is like a 5.5, something like that. Usually in cyclone, we first, if it is up to you to design your cyclone, we first fix the inlet velocity and then we calculate dimension of the inlet. Or you can use this correlation to measure the number of the spirals inside your cyclone. It's very straightforward graph. Okay. Another graph that I want to share with you is about fractional and overall efficiency. So you remember that we said after particles, after TDH, you have to measure size distribution of the particles. So because those particles that are after TDH in the freeboard, they are supposed to get into the cyclone, right? Let's assume that all those particles in the freeboard, they get into cyclone. in other words, size distribution in the freeboard above TDH is similar to size distribution of the stream that gets into the cyclone. Okay. First, why I'm saying that, because these graphs are based on uh, composition of the gas at the entrance of the cyclone. If not, you have to have a kind of correction factor. Let's say, for example, maybe 90% of those particles they get to the cyclone, but this is kind of complicated. We can assume that uh, uh, the same flux of solids and same size distribution of the solids in the freeboard above TPH get into the inlet of cyclone. Then there is this graph that helps you to find the collection efficiency in a cyclone. So you need to have kind of first you have to calculate cut point of the cyclone dp50, and then you need to calculate uh, average of the particles, okay? So like certainty of the particles for each size cut, okay? Because you have different size cuts. For each size cut, you get this value. You come here, you find the efficiency, overall efficiency. But this gives you the overall efficiency for each size cut. Since you have different size cuts according to size distribution that you have, the overall efficiency is the summation of mass fraction of each size cut multiplied by overall efficiency of that size cut. Okay. So here we show the mass fraction by XFI. Okay, as F means feed of the cyclone. But as I said, if you assume that size distribution in the freeboard above TDH is same as size distribution, inside the cyclone, so X infinity and XF are similar. So that's why I'm emphasizing. But there is one problem in this graph. It is just a function of size of the particles. Okay, average size of the particles are in each size cut. But in reality, we need to also consider concentration of the solids. In other words, a flux of the solids in the gas in the mixture of the gas and solid stream. Therefore, you have to have a kind of correction. So what you do for each after you calculate the overall efficiency, you need to take into consideration the flux of the solids that are coming to your cyclone. Remember flux that we calculated yesterday? Yesterday we showed by F infinity to just say that this is the flux of solids above TDH. But since here is about the cyclone, that's why we are showing by flux of the solids. But in fact, this Fs you can assume is same as F infinity calculated in the design of freeboard. Okay, so but since this graph is x-axis is it is like a kilogram per cubic meter of gas, you need to multiply the flux by density of the gas and then divided by flux of the gas, so that the overall unit is going to be kilogram over cubic meter. So after that, you find you locate the value in the x-axis. You go to overall efficiency that you had calculated from previous slide, and then you find the corrected efficiency that is corrected efficiency that takes into account the solid loading. Because here in this graph, solid loading was not considered. It was just efficiency based on size of the particles. But in fact, load or flux of the solids is also important. So that's why you need to have this correction. So you calculate this, you come here, and that's it. Okay, after this introduction to some design aspects, let's see what should be the procedure. Okay, procedure for the cyclone design. First, you can select number of the cyclones. Okay, the very first thing. When you want to design a cyclone, let's say you want to have only one cyclone, and number of cyclones. You can start with one, or you can say no. I want to select two cyclones. It's up to you, but there is a checkpoint that you have to make sure that checkpoint is met. Let's say anyway, you take a value for number of the cyclones. Let's say two cyclones. So based on mass balance on gas, so you have number of cyclones multiplied by flow rate in the inlet. Of course, should be the total flow rate, massive flow rate that you have. It's massive flow rate. That's why you have the density of gas here. Okay, so first you do this because later you will see that in this equation you have inlet velocity and dimension of the entrance. Remember I said the entrance is width of the cyclone multiplied by height. Usually we consider rectangular geometry, not cylindrical. You can say cylindrical, but most of the people use rectangular because tangential velocity that you want will be better obtained. Okay, next step is to set a value for VI. Remember, I said many times today. First, we fix a value for VI. You say, I want to have entrance velocity at, let's say, 25 meters per second. Okay, you do it, but then you will see later if the assumption was a good assumption or not. Okay, also remember that in the Zen's model, for example, we said height of the entrance could be 2 to 3 times width of the entrance. Okay, so by having this ratio, putting everything into this equation, width of the inlet can be obtained. Okay, it can be obtained. Okay, by this equation, just a rearrangement of this equation. After you found the length of the width of the entrance of cyclone, according to Zen's model, just to remind you, this one, you see, Zen's model says width should be 1/4 of the diameter of the barrel. That's why we come back to this equation. We could calculate the diameter of the barrel. Okay, here is the checkpoint. If remember, I said let's make sure that diameter is less than 1 meter. If your diameter was more than 1 meter, you have to come back and increase number of the cyclones. Okay, then you continue. Anyway, after you calculate the dB, diameter of the barrel, then you calculate number of the spirals. So number of the spirals is obtained. Obtained from this equation, from this this curve. Okay, because you need number of spirals to calculate dp50. Remember, because we calculated residence time. Just to remind you, if you want to calculate dp50, you have inlet gas velocity, LW, and number of the spirals. So you need to know this one. Okay. By the way, let me just say that if you calculate VI, if eventually you calculate all efficiencies and you see that efficiency was very low, I'm gonna explain later. You have to later come back to change the gas velocity. But just keep in mind, for instance. So you calculate dP, and then for each size cut, you calculate dPi over dP50. Okay, for each size cut, dPi is just like a average of each size cut divided by dP50, because you need this to calculate overall efficiency of each size cut. After that, you calculate the overall efficiency of all particles by this equation. Okay, that's it for now. Next, if you remember, I said you need to apply a correction factor because you need to consider loading of the solids entering the cyclone. So you calculate Fs rho g over Fg, and you get to this graph by having this ratio. You get the EO, and you find what the corrected overall efficiency. Okay, this is about overall efficiency. But then there is something that is still missing. It is about those particles that are not collected, or other words, escaping solids through the exit pipe of the cyclone. So if we say this is flux of the entering solids and this is the overall efficiency, by this equation you calculate the flux of the solids that exit your cyclone. Okay, so the ratio is kilogram over second. If you want to show, for example, solid loading mixed with the gas, in other words, concentration of the solids in the gas, you can just calculate, multiply by rho g divided by flux of the gas to have this ratio in kilogram per kilogram of solid per cubic meter of the gas. Just a solid loading. Okay, but then it's very important here. What is the size distribution of the solids that are escaping your cyclone? Here, where was it? Oh no, sorry. Yesterday we said we showed you how to calculate size distribution of the particles in freeboard above TDH. And now the question is, what is the size distribution of the particles that are not collected in the cyclone? As a result, they are escaping the cyclone through the exit pipe. So it's very easy to calculate. Since you have the size distribution, mass fraction of each size cut at the entrance, by just taking the overall efficiency of each cyclone, EOI, not EL, EOI, you can calculate XEI, mass fraction of the exiting solids, just by this simple equation. That's it. But something interesting. If for any case you realize that you have to have a secondary cyclone after the primary cyclone, okay, in series. So therefore, these FSE and XEI values that you calculate, in fact, are going to be the feed of the secondary cyclone. Okay, so then you have to follow the same procedure for the secondary cyclone by assuming that exit condition of the first cyclone is the inlet condition of the secondary cyclone. So okay, This is just an example. So fortunately, I shared with you this design calculation that I did long time ago. Everything is here. Don't worry. You just follow my notes. Everything, all calculations in this chapter are here. You see, mine for cyclones, primary cyclones. You see, I calculated everything. I assumed at least first guess I assume I'm gonna have two parallel primary cyclones. I did some calculations, and then I noticed I found that dB was 1.5, more than 1 meter. So I changed number of the parallel primary cyclones. After a couple of calculations, I noticed that I need to have 5 primary cyclones. I can, therefore, I obtained that dB eventually was 0.975 meter. So I said, okay, that assumption was right. And then I can continue. All everything, all calculations are here. And you have to do the same thing. So see, for each size cut, I have the mass fraction of each size cut from freeboard design. Then I did XF divided by DPI in order to do the average of the particles. Then I said DPI to DP50. I calculated for each size cut. Then I calculated overall efficiency for each size cut, and everything's here. But what I want to say is that you see, for each size cut in the primary cyclone, I have 100% efficiency for some of them, but for the finer particles, I have low efficiency. Okay, so I did calculations, and I figured out which ones will go outside. So these ones, you see, the larger ones, I'm sorry, these ones, see, the mass fraction are 0 in the exit. These ones are completely collected in the primary cyclone. You can assume even this one, but the rest, all the particles with this side distribution should go to secondary cyclone. So I did I did all calculations, and the efficiencies. Yeah, you see, at the end, if those in the secondary one, you see that I obtained this kind of efficiency that I could have. Okay, you see that for finer particles, if the efficiency was not close to 100%, it's even less than 90%. Okay, so what I can do, which I didn't do for this project, but what you can do is go back to design and change the assumption of the inlet velocity. Remember, I said inlet velocity, you fix it at the beginning and then you continue your calculations. I'm talking about here. I'm talking about VI. I said set a VI at a reasonable value. If you do all calculations and you realize that your efficiency is not high, You can come back and start over. You can uh, select a new, like a higher velocity, and to do that. Okay, it's up to you. Based on which you will select others. But for
I have a
the
question.
exam, for just a moment. But for the exam, of course, I will tell you what should be the value for your exam, because. But for your project, you need to work on it. What value you have to have to continue your calculations. Hassan, yes, you have question?
Oh no, it was Brian.
Brian, yes.
Yeah, sorry. Maybe you mentioned it and I missed it. But I'm gonna ask again. What would be considered to be a high efficiency? So let's say if we get a value of the efficiency and consider it like too low, what would
Cost,
be like the minimum?
cost, operation cost. I mean,
Oh,
you know, if it is important for you to have, very good question actually, is about the operation cost.
okay.
If you are dealing with expensive powders, you don't want to lose them. You want to have 99% the separation. Okay. But if you are dealing with some not very expensive material, if your solid powders are not very expensive, no problem. So first is the cost. Second, second is environment. If you are producing too much dust, okay, so you don't want to release them to environment, city council will chase you. So this is so the city will tell you, okay, you have permission to release, for example, 100 ppm of the particles to the environment. So you have a fixed value from environmental agency, whatever city council, or whatever agency around you. So you have to have below that limit. So first is cost, second is environment. The rest uh, is just calculation. Did you get the point?
Yep. Thank you very much.
Yeah. But it was a very good question, actually. So let's have a break until 4 o'clock. We come back and I finish the rest about the cyclone pressure. But the design, anyway, for the design of the cyclone, I really want you to go to this calculation I have done. Very, I'm not saying I did a good job, but very clear what everything is very clear. You can easily follow up all the step-by-step calculation, and then there you go. You have no problem to understand. But can you confirm that you have my report?
Yes, you have it.
I'm talking about this report. Yeah, 2000,
Yes,
April 20, 2007. My gosh.
yes, you have it.
Okay, let's be back at 4 o'clock. But if you have questions, feel free to ask. Okay, so do you see my screen?
No.
No.
Really?
Yes.
Okay.
No, we see.
Okay, now you see. So we talk about the importance of cyclones and design of cyclones. So you should go to course notes to see how we can design a cyclone, but even pressure drops. In fact, in fluidization, uh, pressure is a very important thing. Very, very important. We have, because from the wind box to distributor to freeboard, cyclone, everything back, if we want to have a good flow, as I said, we are talking about solid powders and we want to have them in a fluid mode. It is very important that you make sure you take into consideration the pressure drops. You calculate pressure drops at each single point. So at the end, whole process is balanced with pressure. Okay, so in cyclone, from the entrance of the stream of the gas and solid uh, until the bottom of the cyclone, uh, you have different pressure drops. Pressure drops. So a pressure drop of a cyclone can have 5 different terms. Acceleration of the gas, acceleration of the solid, both are at the entrance, pressure drop inside the cylindrical barrel, pressure drop when the gas starts its reverse flow toward the exit pipe, and also pressure drop when the gas exits the pipe, gets out of the exit pipe. Okay, and there are correlation for these values. I want to go quickly, very easy to just follow. So for the acceleration pressure drop, we can use this equation. I think you understand why it is acceleration pressure drop, because the all from the freeboard, all the stream wants to get into the entrance window. So you have a kind of contraction of the gas from a vessel. So that's why you have that kind of acceleration. So the formula is this, okay? But you have two velocities here. This VGI is the same VI that we discussed before, the entrance gas in the cyclone. But this velocity is superficial velocity inside the reactor, in the freeboard, okay? Mentioned here, okay? I'm using VGI to just say that it's a gas velocity, not a solid velocity. But so this is the entrance velocity in the cyclone that you take, and this is the velocity of the gas in the superficial velocity of the gas in the freeboard. For acceleration of the solids, okay, okay, again, this is the formula that is used by this gentleman Zenz again. But you know, he used in the correlation WS, but WS is the same as F that we talked yesterday. It's the flux of the solids, F. But it shows by Fs, but it's the same as F infinity that we have uh, in the freeboard. I'm intentionally we are showing different parameters because not necessarily the flux of solid in the freeboard is the same flux in the cyclone. Uh, so, but you can make the assumption that almost the same thing. And these are the slip velocities of the particle, and okay. But since the slip velocity is gas velocity minus thermal velocity, so you can say right. You can use the same velocities: gas velocity in the influence and gas velocity in the freeboard. So very simple correlations. And if you follow my report that everything is calculated, you can easily follow up. So there is also a pressure drop inside the barrel. So you know that already. So barrel is like a tube. Already you know from the fluid mechanics that the pressure drop inside the barrel, it follows this kind of correlation. We can easily calculate, but since in fact that stream, that the spiral is like a rope, so you need to have, if you want to have a kind of if you want to have a kind of uh, um, correction for the inside the barrel, you need to calculate equivalent diameter of the rope. Okay, so it's obtained from by this equation. Anyway, you follow this correlation for to follow the calculation. If I want to go to detail, it takes a lot of time, but it's very easy to understand. Another in this equation, you have this friction factor. So this friction factor is obtained from these equations, these correlations, very easy to follow. The only thing is that this RW is about roughness of the wall. Okay, we can take if we have if the barrel is the soft, we can take a 0. But the thing is, as written here, this roughness could change by time because some solids stick to the wall of the cyclone. They stick forever until you make it cleaning. So that roughness could be even more than the 0.05 millimeter that mentioned here for the stainless steel. You can take maybe zero point 0.1 or 0.2, but again, it's not a big deal. It's a pressure drop. So for the reversal of the gas, so the delta P is calculated by this value. So as a spiral velocity or inlet velocity of the gas, this is the density of gas, and also pressure drop at the exit of the cyclone. So here you have two velocities. This is velocity inside cyclone exit pipe. This is the velocity. Oh, sorry, my mistake. This is the velocity at the uh, entrance of the gas to the exit pipe, and this is the velocity inside the barrel. So you can say that so this velocity could be the same velocity as VI or VGI that we take in other correlation. You can assume that VE is same velocity as superficial velocity that you have. Roughly, they say you can take this ratio same as a ratio that you need for pressure drop at the entrance of the cyclone, just roughly. Okay, but okay, these are some general information about the cyclone pressure drop. They say that these are just correlations about pressure drop. Of course, uh, there are more advanced correlations for pressure drop measurements, but the most uh, uh, reliable method for to control pressure drop is to put pressure gauge. I mean, pressure transducers, one before cyclone, one after cyclone. I'm sure Job will talk to you about the measurement techniques. You can put the pressure transducers, measure the pressures, and just kind to have a better idea of the pressure that you can get, and then verify with the correlation that exists. Okay, but something important in the cyclone is the selection of lengths of the cyclone. If you remember, I said I'm not feeling, I don't feel much personally very comfort. I don't feel comfortable that some people have correlations for the conical zone. Okay, this correlation. Because why? Because in fact, this zone, this conical zone, should be, in my opinion, selected after you have an idea about the length of the vortex. The length of the vortex, which shown by L, is where gas starts to have the reverse flow. So after gas gets down, then change its direction and then goes high. So length from here to bottom of the exit pipe. This is the vortex, or we call it cyclone length. Why is it important? This is important because, you know, if uh, if you design a cyclone like this, okay, you just go to tables and get the dimensions and design a cyclone with this geometry. But in reality, your vortex is going to be like this, so that the spiral goes all the way to the bottom of the conical zone and then reverses upward. The problem is the particles they are touching the conical zone, and they can erode the conical zone. Usually, we want to have a system where touch between the spirals and the conical zone is avoided, especially specifically for larger particles. Okay, we want to avoid it. So that's why it's important to first have an idea about the lengths, okay, and design the conical zone below the L, below the lengths, below the L, okay. And then even the conical zone itself, the angle should be set first by the diameter of the deep leg pipe, okay, and then by knowing angle of repose of the particles, you decide what should be the angle here. Okay, so it is important to have length of the cyclone. Already I mentioned what is written here. The only thing in the second paragraph, in this paragraph, is that about this paragraph says that if you are dealing with cohesive powders like group C particles, maybe it's not bad if the vortex touches the conical zone, because it helps to prevent agglomeration of the cohesive particles. That could be just one exceptional case. But the thing is, if cohesive particles touch the conical zone, they may get stretched. If they get stretched, again, they may, uh, they may impact the efficiency of the cyclone. So therefore, maybe you can put some liners, some buffers to avoid the stretch of the particles. Just back to discussion that we had about these lengths of the cyclone. Okay, I just want to show you again that if you have not enough length, okay, you end up with this kind of vortex. So this picture shows you kind of a streamline of the vortex. If they can go all the way down, and not only they can erode the conical zone, but also they can re-entrain the particles that are supposed to be collected. So those collected particles will be re-entrained with the gas, and they go to the outside. So therefore, this length is very important. There are some correlations for the length of the cyclone, so you can go to notes and see which one is more interesting. The first one is not really a good it's not a good correlation, because it predicts that if diameter of the exit part is reduced, L will be reduced, because usually the opposite term is correct. So this is not, it's very old, 1949, imagine. But recent correlation are more acceptable. Is either this one or this one we can take to calculate the length of the cyclone. So again, my point is you need to calculate the length of the vortex. Okay. So after all dimensional calculations that you do for the diameter of the barrel, diameter of the exit pipe, diameter of the inlet, but I mean width of the inlet, everything, you have to calculate L, okay, which is from bottom, which is about the distance from the entrance to the bottom, okay, and then start sizing the conical part. This is my point. So that's about the cyclone length. Another important, very important topic about the cyclone is deep lake of the cyclone. So we discussed about the cyclone, the conical zone, and now this pipe. This pipe is called cyclone. It's called the deep lake. Why is it important? As I said before, usually deep lakes are recommended to be immersed inside the dense bed. Okay, but what happens is that some of the particles, even the thing is, due to the pressure, you have a, unfortunately, here is not clear. In fact, here is the level, here there are powders. These powders that are supposed to fall through the deep lake, okay, in fact, they make a level here inside the deep lake, okay, because of the back pressure from the bed to the deep lake. So you have always a height of the solids inside the deep lake. So therefore, by considering this kind of situation, you have three heights, three static height. One height is from the bed surface to entrance of the deep lake, okay, which is here. One height is from the bottom of the deep lake to level of the particles in the deep lake. And one height is from bottom of the deep lake to the bed surface. There must be a, uh, a kind of pressure balance between these three heights, because it is important that uh, especially this height, HD, the height of the powders here, okay, doesn't get to the uh, conical zone of the cyclone. So for that reason, we need to make a pressure balance. So if you write the pressure balance around the cyclone, okay, so rho d HD equal to density of the bulk, HS, and total cyclone pressure drop divided by G. You can calculate, you can see that static height of the material inside the deep lake can be equivalent to this ratio. So, but to be safe side, it is usually suggested that H, okay, H should be almost, if you write if you write this term in other words, usually they say roughly is better that height, okay, should be more than 1.5 plus HD minus HS. I mean, usually they say this H should be more than HD minus HS plus 1.75 meter. This is the rough kind of estimation for the position of the uh, for the length of the deep lake. Because when if you let's say whatever you select for the immersion of the deep lake, so you want to immerse the deep lake inside, you have to make sure that the rest of the length of the deep lake H is following this correlation. But the one important thing about I have to come back about the material inside the deep lake is that some people may think that uh, material here is same as material inside the dense bed, but it is not the case. In the dense bed, density of the bulk is not the same as bulk here. These powders here, even though some gas could be inside. Usually, we assume that the bed here in the cyclone, I mean the bed of the material inside the cyclone deep lake is like has a density of the at the minimum bubbling fluidization condition. So they say, as mentioned here, they say that density inside the deep lake is density at minimum bubbling fluidization, because uh, concentration of the solid here is definitely more than concentration of solids here. Roughly, you can say uh, uh, density of the material in the inside the deep lake is about rho mb. So you need to know just an estimation of the density of the bed at minimum fluidization velocity, minimum bubbling velocity. You know that uh, uh, dense, bulk density is particle density multiplied by 1 minus bed voltage. So if you know the bed voltage at the bubbling fluidization velocity, minimum bubbling fluidization velocity, you can take that value, which could be something like bed voltage at minimum bubbling could be zero point 0.5, something like that. Okay, this is about a deep lake, position of the deep lake, but most important thing is this one, most important thing for the position of the overall position of cyclone. Length of the cyclone and height of the deep lake above the dense bed should be more than TDH. Okay. In other words, if I come back to this figure, some people may easily forget about this kind of pressure balance around the deep lake. So they just calculate TDH and they say, okay, interference of the cyclone can be right away after TDH. But this is not the case. Because usually you have this height is the one that governs the position of the cyclone. So of course, definitely, this height should be more than TDH. If you calculate H and H is less than TDH, so definitely you have to put it at at least minimum TDH. But most of the time, this H will be automatically more than TDH. Okay, and it is important that you calculate this height, which is the length of the deep lake outside the dense bed, plus length of the cyclone L that we discussed, and the cyclone should be a minimum at that position. Okay, so this is about the deep leg of the cyclone. I think I missed something. Since there is no time, I'm a bit in rush, but I have to slow down a little bit. There are some general comments about the size of the deep leg diameter. In general, the deep leg diameter, the pipe of the cyclone, we say is should be minimum 10 to 15 centimeter in general. For industrial case, deep leg should be 10 to 15 centimeter. Okay, and to be on the safe side, you can assume that the powders they follow by the gravity. Okay, but in practice, usually since solid become aerated because of the backflow of the gas to the deep lake, the flow is roughly okay, and especially if the powders are group A powders, you should have no worries about the falling flow of the solids inside the deep bed of the cyclone. But what you have to consider, okay, is that you should ensure, okay, the gas from the dense bed cannot flow through the deep lake and into the cyclone. You have to make sure that the gas cannot get into. And this is why usually uh, we have uh, those uh, kind of check valves or Philippine kind of uh, uh, doors at the bottom of the deep lake that we are going to show in the next slide. You should not have a flow of the gas through the deep lake, because otherwise uh, the cyclone can reach to a balance with the dense bed, so the cyclone will not operate at all. So all the gas that is from the dense bed can come to the deep lake. So this is something that we need to pay attention. Another one is that, I mean, uh, as a conclusion of what I just said, the downward velocity of the solids in the deep lake must be always larger than two things. First, upward velocity of the gas that percolates through the emulsion solids. As I said, anyway, some gas um, um, some gas anyway can come to the deep lake from the dense bed, but the velocity of that gas should be definitely less than velocity of the falling particles. First, second thing, you should make sure that um, uh, because deep lake is a small diameter, as I said, 10 to 15 centimeters, so you may have kind of slugging flow. You have to make sure that the velocity of the falling solids is larger than slug velocity in the deep lake, which is by this correlation. Um, Gravity acceleration and diameter of the deep lake. So when you design a cyclone, and you have to design its deep lake as well, and you have to make sure that you have to show that velocity of the solids inside the deep lake is definitely more than this value. Okay? A rule of thumb: solid velocities in primary cyclone is 0.6 to 1 meter per second. Rule of thumb. Okay, I showed you already this right at the beginning. So usually we have some closures at the bottom of the duplex to better control uh, return of the solids to the dense bed and minimize the flow of uh, gas from the dense bed to the duplex. So you can see you have a dollar plate or like a disc plate, you have diamond plate, you have this kind of angle bend pipe, and this angle pipe sometimes it is capped by this kind of flapper. As we saw in the FCC process, they use this option. Okay, this was about cyclones, but I want to say something. Oh yeah, these closures. I'm just remind you again. These duplex closures are shown here in the FCC. You see that for the primary, they use this kind of Chinese hat at the bottom of the blade, but for primary, they use this kind of flapper valve. So this is just a design option depending on the process. I want to just 5 minutes talk about something extremely important that we didn't have time in the course to discuss, but I just want to give you an idea. So if you pay attention to cyclone, let's say this is a reactor, this is cyclone. So you have always a flow of the gas and solids go into the cyclone. And then solids are recovered, they're separated and they're recovered through the deep lake and get back to reactor. So you have this kind of circulation of the solid. You have this kind of circulation of the solid between the dense bed and cyclone, right? Uh, you notice that in order to have this kind of circulation, we need to definitely consider a pressure drop and a static heads according to this correlation. So you have to always have a pressure balance between cyclone, dense bed, and deep lake, okay? And to make sure that you have a good flow of the powders. In fact, in practice, we have several fluidization systems that are in circulation mode, which means solid powders they travel kind of circulation between two reactors, between reactor and a cyclone, and the other configurations. We don't have enough time to go to circulating fluidized beds, but I just want to show you that in any circulation system, one parameter, as we saw in the case of cyclone, is the pressure balance. If you, for example, consider this system that has a kind of transportation line, and then everything, all the powder, they come back to this kind of downer reactor, is a downer, as opposed to riser, we can have downer columns. To this downer column, if you see, there are several points that you have pressure, that you have a pressure change, the pressure drop from the point number one, where feed is injected. For number two, here you have a expansion pressure drop. From three, another pressure at point four. There's a contraction pressure drop here. There are a lot of pressure. And if you plot variation of pressure versus height of the reactor, height of the process, you can see that profile of pressure is following this kind of curve. Okay, so at the end, you can see that there is a higher pressure at point 9 and lower pressure at point 1. Where you have a valve. You have a valve that controls the flow, that controls flux of the powders to point 1. Always this kind of pressure profiles should be plotted in around the circulating fluid. In case you design a system and you find that you see that the pressure is not balanced, you have to balance it by using a compressor, pump, or this kind of valves to sustain that pressure drop. Okay, so you saw the same case for the FCC process. Remember, in the deep lakes, you had some valves to control the flux of the solids. The same thing. Another example is this kind of coal combustor reactor. So this is the bubbling fluidizer reactor for the coal combustion, and all the powders, they go to an external cyclone. This external cyclone is designed in order to recover uncombusted coal powders, okay, and also maybe some fly ash at the bottom, okay. So and then by a specific deep lake design, unconverted coal powders, they get back to main reactor. Again, you see that from point number 1, which is below pressure drop, you start, you have, by the way, the main thing is start on position 10, because number 1 and 11 are the before and after distributor, but the main operations are about number 10, because the loop is from here. You see that the pressure drop is maintained from 2 to 3, 4, 5. Pressure increases at 6 and then decreases at 7, slightly decrease at 8, and then increases at 9. So pressure at 9 increases. Why? Because it has to be pressurized to be pushed to number 10. So your valve can be used here to push. Okay. So in any circulating fluid as well, these pressure profiles are very important. And the last example is the FCC process that we discussed. You can leave it to yourself to follow up, but you can see this standpipe valve here. Okay. So if you want to know, for example, what type of valve you require, so you need to know what kind of pressure drop you are going to have through the valve. So you have to write the pressure balance, okay, from between the generator and the riser. Okay, as you see, this is the to obtain the pressure before and after the standpipe valve to get an idea of that valve, and then you go and buy the valve that you want from market. So this is more complex than what we are showing you here, but just to give you an idea about circulating fluidized and importance of pressure balance and to make sure that that the flow of the solid can be maintained. But this circulating system is not part of your course, but for your project design, in case it is you have to deal with the circulating fluidization, you have no choice. You need to consider this kind of pressure balances. So this is about fluidization course. I hope you guys learned something about fluidization. And let me stop this.